Hey, this is Tony from Adafruit, and in this video this is part 2 of the Circuit Walker Sneakers project, and this is the project to use Circuit Playground to animate your sneakers and basically glow different lights and sparkle and do cool animations every time it detects that you take a step. So you can see as I move this sneaker as if I was walking in it, it lights up every time I kind of come down like that. So like I said, this is part 2. There was an earlier part 1 video that I did where we look at this adaptive step detection algorithm that uses accelerometer data. It was originally written for Android phones, but we saw how just using that algorithm we can apply it to Circuit Playground, which is Adafruit's all-in-one electronics learning board that looks kind of like this. And so this board has an accelerometer built into it, and then also a little ring of neopixels and other sensors and things on it. So it's great in that everything is built in, and if I just attach this to a pair of sneakers, like this pair of really cool Converse shoes I have, check that out, they're kind of circuit board themed. They don't make these anymore, they came out with them for just a few years. But I zip tied this little Circuit Playground onto the laces here, so it's nothing fancy, like this is not permanent, I can pull this off. But it's really cool in that I just put this on my shoe and then suddenly it's like the Firewalker sneaker project, which I talked about and is linked from in the first video. So definitely check out the first video if you haven't seen that one yet. So in the first video, like I said, I look at the algorithm and the first part's the algorithm where you basically take the accelerometer data, which tells you the forces of gravity, like what forces are being applied to the accelerometer itself over 3 axes. There's an X, Y, Z axis. So it can tell kind of its orientation, but you use that data to figure out when a step is taken. So you look for kind of this regular motion, this up-down motion of your foot moving to detect the steps. And so we looked at how to do some filtering and apply some basic thresholds to get a really rough and quick and dirty version of the Circuit Walker sneakers. And actually I'll show you, this was the version we built in the first video. And so this one's a lot simpler. You see there's no animation on this one. So in this video, we'll see how to do this animated version right here that has a neat little rainbow effect. But in this first version, you see it works pretty well. Now it's hard for me to demonstrate, but this version is not as good as this version that I'm going to show in this video here. So the rainbow one is actually using a different algorithm that uses this adaptive step detection, whereas the red one, what we did in the first video, this uses a simple threshold detection. So this red one needs a little bit of tweaking, like what we did in the first video. If you take a very soft step, like notice, I can move this thing around, and if I just very slightly move it as if, I was just taking a very light step, it's not detecting that. You have to take a strong step in order for it to detect the motion. And so it's not a very smart algorithm in the sense that you kind of have to tell it ahead of time what your steps are like. And that's not bad. You can tweak that and tune that value, and it makes the code a little bit simpler, and it doesn't have to have a lot of this logic. But the cool thing is with this version right here, the rainbow one we're going to look at, the final version of the Circuit Walker sneakers, it's adaptive. And so you can see as I hold it, I'm kind of moving it around a little bit. And so it does get a little bit more of what I'd say maybe a false positive, where it's, falsely detecting a step. But it's kind of nice in that, if I just do a real soft motion, notice as I move it down, it's detecting that as a step, and that's exactly what I want. But I can also do a large movement here. So, large movement, and as I come down, it's detecting that as a step, and it's lighting up, so soft movement, and then also large movement. And so this is really nice in that I don't have to tweak anything. I load this code onto the Circuit Playground, I put it on my shoes, and it's ready to go. There's no tweaking, unlike maybe the very first version of the Firewalker sneakers where you had to set some of these resistance thresholds and things. This one's pretty cool. It's all in one, and it learns from the data that it sees with the algorithm. So we'll dig in and we'll see. I think what I'll do is I'll start with showing how to load this version of the Circuit Walker sneakers onto a Circuit Playground. So if you just want to use these and just have fun and just get these cool rainbow effects and you don't really care how it works, stick around. I'll do that in the very first part of this video. And then in the second part, or maybe in the next half of this video, I'll dig into the code for this version. And like I said, it's an adaptive algorithm. So it's basically a better version of the algorithm we looked at in the first video. And maybe I'll also just show some of the rainbow animation effects that I added right here. So it was a neat little addition to the basic animation I did in the first video. So let's dive in. I'll switch to the main view. And like I said, I'll start with just showing how to load the Circuit Walker sneakers sketch. So I'll show you where to find it and how to install it. And so that's the version right here. That's kind of this rainbow version. What you want to do, let me open up the code for this. So the code for this is in this GitHub repository, this Circuit Walker Sneakers repository on Adafruit's account. I'll put a link in the description when this goes up on YouTube, so check below and there should be a link to this GitHub repository. Now if you don't care about anything and you just want this thing to work and you just want to run it, you want to grab the Arduino Circuit Walker sketch inside of here. So there's like 4 or 5 Arduino sketches inside of here that kind of show the evolution of this sneaker project. So if you watch all the videos, you'll see all the different versions of these and what they mean. But Arduino Circuit Walker, this is the version you want if you just want this code. So download this repository. And then you'll need to get Arduino set up. You'll need a Circuit Playground board, obviously. So this is the classic board that I'm using, but this also works with the Express board, which is the newer board. So you need one of those, and you need Arduino set up to program that board. So check out the guide for your Circuit Playground board, and it'll tell you how to install like a custom board package so you can program with Arduino. And then you should be okay. You might need to also install the Adafruit Circuit Playground library. So if you go into let's see, where did they hide that thing? The library manager. So if you go into Manage Libraries, search for Circuit Playground. So if we filter to Circuit, see at the very top here, Circuit Playground, make sure to install the latest version of the Circuit Playground library if you don't have it already, just to make sure you get the very latest and greatest code for that. But like I said, so we need to download this GitHub repository and open up the Arduino Circuit Walker sketch inside of there. So that's what I will do. I will just open up in Arduino. We'll grab from my GitHub repositories the Circuit Walker sketch right here. And this will open it up. And there's really nothing you need to change. So there are a bunch of defines up at the top right here. If you want to change the animation, so like notice, you know, when it detects animation, you can see it kind of moves around in a rainbow. So the speed of that animation is defined by this animation frequency in hertz. And basically if you increase this, it will spin around faster. So if you set it to 2, it'll spin around twice as fast. If you decrease it, if you set it to like 0.5, it'll spin around slower, so like half as fast with 0.5. So if you want to speed it up or slow it down, that's what you can do. And then this step flash milliseconds. This is the amount of time in milliseconds that the animation will light up. And notice how it kind of fades out. So if I tap this, it gets real bright and then it fades back out. And so over that period of 500 milliseconds, which is half a second, that's when it's lighting up and then fading out with its animation. So if you want to make it light up and fade out for a longer period, increase this value to like maybe 1,000 for a second, or if you want to make it a shorter period, decrease it down to like 200 milliseconds, you know, whatever you want to set. So those are maybe the most interesting values to change. The next values you don't really need to change, and if you want to understand these, stick around and watch the whole video and we'll dig into what these things actually mean. But these kind of control that adaptive jerk step detection algorithm. Basically this initial jerk is a value that it uses to kind of bootstrap and pick an initial average jerk, and the jerk is basically the change in acceleration of the accelerometer value. So it's effectively taking the derivative of it, or looking at, you know, how does that acceleration value change over time. And so it's looking at that change, and it starts with an initial value, and then this alpha and beta define, these actually are blending parameters that define a weighted average, because over time it updates that average jerk value with a weighted average, depending on if it detects a jerk that's greater than some number of standard deviations beyond the current average. So if it gets a really strong jerk, then it will update that average value. And so that's how it adapts itself over time, is that it's changing this average jerk value to figure out, okay, you know, I just saw a strong impulse of acceleration. Was it strong enough? Did it go past that average jerk value or impulse value that I've seen before? And if it did, then it will fire the animation effect like you see right there. And then it will also update that average. And so that's how, like, if you're a very soft stepper, over time, that average will decrease. It's going to fall down, down, down. And then eventually it's going to figure out what threshold your steps look like as you take enough steps with that. Whereas if you switch to taking really strong steps, you're just going to keep pushing that average up and up and up until it's, you know, at a steady value that it's figuring out what your steps look like. So kind of cool how it changes that way. And then this gravity value, this is basically a threshold for figuring out if it's increasing or decreasing, like if your step's going up or down, because basically you're going to have a value that's higher than your relative gravity value, because just standing here on the table, it's seeing 1g of acceleration straight down. So basically straight down, that's just the force of gravity coming down. It's always going to be here. As long as you're on Earth. If you go to the moon, that's going to be a different value. So I guess if you're running this sketch on the moon, which 48 years ago might have been possible, that was when Apollo 11, I believe, it was around this time in July that Apollo 11 was on the moon for the first time. So if you're on the moon, you will probably need to tweak this down to, I believe it's 0.66 or something like that. It's maybe 0.33. It's certainly lower on the moon. And on Saturn and Mars and other planets, I don't know, you're gonna have to look up accordingly. On Jupiter, this is gonna be high. This is gonna be like, I don't know, 10 times, 100 times the gravity? I have no idea what it is. Anyways, you probably don't need to change this if you're on Earth, so stick with the 1.0 value. The sample rate in hertz, this is how frequently the accelerometer is sampled. Stick with this 50 hertz value because there's all this complex filtering. If you go back to the first video that we dug into, it depends on this 50 hertz sample rate value, so stick with that. Everything else you don't want to change. This is all just the code for this sketch. Some of it might be familiar from the first video. There's this infinite impulse response filter that does a 3.66 hertz low pass Butterworth filter. And so that's used to basically smooth out the accelerometer data. And then I do all this fanciness in here. I'm gamma correcting the color of the neopixels, and we'll dig into this more later in the video. So net result here is load up this circuit walker sketch. Maybe if you want to play with the animations, tweak these first two little define values. But otherwise, that's it. So I'm going to plug in this top board. This one was running the red example, so that's like our initial version. So I'm going to plug this in. And then I'm just going to make sure that it has the Circuit Playground board selected. So yeah, there's the board. And a quick little tip, when you install Circuit Playground, be careful because Arduino in the latest versions have a version of Circuit Playground. You might see Adafruit Circuit Playground, but this is listed under Arduino AVR boards. You don't want to use that because that uses an older version of the Circuit Playground library that might get confused. So make sure to install the Adafruit board package like the Circuit Playground guide shows how to do, and then pick the Adafruit Circuit Playground board. I think with the next version of Arduino, they're going to fix this so that there's not this weird library issue. But just to be safe, always use the Adafruit package version right here. So that's what I have selected, and then the serial port for it figured out. So let's click upload, and we'll push this up to our Circuit Playground board. And that's the nice thing about Circuit Playground, though, is that, the board comes like this. Everything is soldered to it. I don't have to wire anything up. I don't need to connect anything. Like literally all I did was just run a zip tie through two of the outside pins. You can see there's some holes on the outside of the board. I just ran a zip tie through some of the holes right here. Oops, let me see how to, there we go. So you can see that, and just zip tied it to the laces on some sneakers. So that's one easy way to mount these. Actually, this board I put on the back. You can see there's this little clip right here. This is if you want to clip it to clothing, so you could do that. That's actually the cool thing about this step detection algorithm. It doesn't have to be on your shoes. It can actually be on your body or your person or your arm, and it's still able to detect the steps, and it's still going to animate and flash. It's kind of cool. You can get really creative with this. Okay, so I loaded it up, and that's actually it. So I'm just going to unplug it, and it's got battery power running, but you can see it's starting to do its thing. So, and like I said, when it's a little bit noisy, so when you first hold it, because the algorithm is adapting and it's changing that average, it's very sensitive when it first starts up. But then as you get into kind of this regular movement of motion like this, it's usually on the kind of the downstroke, right when you get down and you hit the floor and you're about to pick your foot right back up again. That's when it starts to detect the movement and when it lights up. So you can see that, and it should be smart enough. So I can take strong steps like this and it's able to detect that. You can see at the bottom of the step it lights up, and then if I take light steps, it will, it's a little sensitive at first, but then over time now it's getting, it's kind of honing in on what that average value is, and so it's firing off on the downstroke there. So really cool. And that's it, you're done. So that if you want to just play with this, get a couple Circuit Playgrounds. Like I said, you can just see I've zip tied them onto the board. There's a zip tie right here. Be careful though, because if you're looping through the outer pins of the Circuit Playground board, some of these pins are the output of your battery, and some of them are ground, and you don't want to short those out. So like this is a plastic zip tie that's not conductive. If you're using like a piece of metal or something, be very careful which pins you go through, and maybe don't even use the pins if you're using something conductive, just to make sure you don't short something out. As far as how I'm powering this, I have a little lithium polymer battery that I've jammed inside of the tongue of the shoe right here. Let me see if I can pull this thing out. There we go. So you can see this is just a little lithium polymer battery, and I just jammed it into the tongue of the shoe. Lithium polymer batteries can be a little dangerous. You don't want to get these things wet. You don't want to get them overheated. If they're stuck to your body like this, that can be a little sketchy. So, I'm going to write up a guide on this, and I'll show, we have a nice little 3D printed enclosure you can print to go around the lithium polymer battery. You can also wrap it in tape, or you can even just use one of these things. This is a AA battery pack with a little on-off switch. This is fine. This will power it also. And alkaline batteries, although they're bigger, you'd have to maybe connect this. What you could do is Velcro this to the back of your shoe, and then just run the wire up to the front there. And that would be a little bit safer and easier way to do this. But as long as you get it powered though, then it's good to go and we're ready to run. So okay, so let's dig in. That's it. If you want to use this sketch, that's all you need to do is just load this sketch and on Circuit Playground, and you're done. And it will hopefully tune itself to how your steps work, and you'll see all those fun little animation effects. But let's dig into how this thing works. So like I said, this is the follow-up. In the first video, we looked at the algorithm behind this and maybe the first half of this algorithm. And so in this video, we're going to dive into the second half of this algorithm, how it becomes adaptive and how it learns your step and how it kind of tunes itself over time. So I'm going to close this, and let's see. So we'll start with the original paper that I was basing this on. I'm not sure if this was a paper that was ever published. Maybe it was like someone's school project, but I was just searching around for step detection accelerometer, and this was one of the hits that kind of came up. And it's a really nice thing on GitHub that a couple folks put together that looked at how to do, in the context of the accelerometer on your mobile phone, this step detection. So you keep your phone in your pocket, and then can you detect, how many steps do you take throughout the day? More, I think this is in the context of like fitness monitoring and stuff, but it's still kind of cool that, if you can detect a step, you can do things like these animations. So in the first video, we looked at the very first thing they tried. So this paper goes through about 5 or 6 different things they tried, where they had some ideas, they tried it out, they saw that it maybe worked well for one person, but it didn't work well for another person, and then they refined that idea, they tweaked their algorithm, they tested it out again, they saw how well it worked, until eventually, after 5 or 6 iterations, they get down to a final version, and they actually show kind of how well this version worked, this adaptive step jerk pace buffer version. So we'll see. I don't go all the way down to the pace buffer version of this algorithm. The one that we're looking at on these shoes is the adaptive step jerk algorithm, because pace buffer one, I don't know, maybe in the future I'll play around with it, but this adaptive step jerk one seemed like it worked well enough for me, at least in my testing. Okay, so in the first video, we looked at the very first thing they do in this paper is basically they get your accelerometer. It has 3 axes of data, X, Y, Z axis. We saw that in the first video. You figure out the magnitude of that acceleration. And so that way, the orientation of the board, whether it's mounted to your shoes like this, or if it's mounted like that on your shoes, it doesn't matter. It's looking at the magnitude. It's looking at all 3 axes of the accelerometer. So as long as there's some kind of regular motion, it's able to detect that. But then the next step that it takes is it applies a low-pass filter to the algorithm, to the output of your accelerometer, to that magnitude value. And then we saw in the first video, I actually looked at the output in Arduino, we graphed it, and I had a little IPython or a Jupyter notebook that I put together that kind of showed how this paper built this filter and kind of what effect it has on the raw acceleration value. So you saw the accelerometer values are kind of shaky, and like every little tiny movement is picked up, and you see this real spiky graph, kind of like the red lines back here. But then when you apply this filter, that gets rid of all that high frequency noise, and it just leaves this smoother motion, and that's the green line right here. And we saw that in the first video, and we saw how to implement that in Arduino. I implemented this infinite impulse response filter, which is basically just a bunch of signal processing magic to build this low pass filter. And you get these magic numbers, and when you plug these magic numbers in, it applies this low pass filter with these special parameters. So, the filter is tuned to a certain frequency where it will reject frequencies that are above that value, but it will accept frequencies that are below that value. So it's 3.66 hertz is the frequency, the cutoff frequency for this filter, which means 3 times a second. So that's that makes sense, because when you think of your walking and your movement, it's very rare that you're going to be walking more than 3 times, like taking more than 3 steps a second. 3 steps a second is probably like, you know, Olympic 100-meter dash level of, you know, I don't know if Usain Bolt can even do 3 times a second step, you know, that kind of pace. So if we're filtering everything below 3 times a second, then we should hopefully see all human steps. Although if you're applying this to a cheetah, you might need to change this filter. So, you know, take note, if you're doing this with a cheetah on the moon, you're going to need to change the gravity and the filtering. So just be aware of that. But for humans on Earth, this is probably going to work. Anyways, that's what the first thing they tried in this paper was: apply a low pass filter to the accelerometer and just set a fixed threshold. And that was actually what we saw with the red version of these sneakers, the ones I started with. It's actually this Arduino step test. So if you go back to this GitHub repository, the Arduino step test version is what we ended the first video on. And so we also did a filter test. This one just graphs the accelerometer values. The step test actually turns the lights on and makes them flash red. So that's what we ended the first video with. And that's where the paper got to, you know, right about here with this point, where they kind of said, okay, you filter the accelerometer magnitude, you set a fixed threshold, which this is the step test sketch. This is that threshold right here. And so that's how you pick that threshold. And basically, you know, if it's too sensitive, then you increase this threshold. If it's not sensitive enough, you decrease the threshold. And so you have to kind of figure out what value makes sense for the way that you take steps. So that's all fine and good, and it actually works pretty well, and the code's relatively simple and easy to follow. You know, like I went through this in the first video. And by the way, if you watch the first video, I made a pretty major error in that first video where I forgot to update the elapsed time, or basically the frame time. I forgot to, basically this code wasn't in the first video. And it still sort of worked, you know, I mean, it was flashing and it was detecting the movement, but it wasn't working the way I really expected it to work. So a viewer caught that and emailed me, so thanks a lot for that. But, you know, basically download the latest code and you'll get this fix. But end result here, though, this is the main code for this. And you can just kind of see every 50 milliseconds, so there's this frequency that it samples the accelerometer at. It just grabs the accelerometer, computes the magnitude of it, runs it through that little low pass filter right here, and then looks to see if the filtered value passes that threshold. We detected a step, and so it's going to light up. It'll set a counter that says how long the lights should stay lit, and then just every loop iteration it decreases that counter until it gets down to 0, and then it turns off the lights effectively. So that works really well. But they mentioned in this paper there were basically 2 people. So they had a bunch of data sets where they used an accelerometer and they logged that to a file, and then they could run their algorithm on that output and see how it would work as they changed their algorithm. And so for one person it worked really well because I think he had really big steps, but for another person that same threshold didn't work well at all. The Zong person right here, you know, you can see it was missing some of these steps, like these lighter steps right here. Basically these red dots are where their algorithm detected a step. And so some of these steps right here were below that threshold and they weren't detected. So they thought about, okay, well, how can we fix that? And they thought about, could we look at what's called the jerk, which is basically the change in acceleration? Because previously we were just looking at the acceleration value itself, filtered through that low pass filter, but the acceleration value. And so once we see a high enough acceleration, it goes past the threshold, we consider that a step. But picking that threshold is difficult. So their first thought was, well, what if we take the rate of change of the acceleration? So I'm not just looking at, you know, is it like moving down very quickly? It's, you know, is it starting to slow down or is it starting to speed up? It's kind of that rate of change of the acceleration. And they call that the peak jerk threshold. And what you can do, you can actually use a numeric method to compute the derivative of the acceleration, because if you take the acceleration, if you take the derivative of the acceleration, that gives you the rate of change of the acceleration. And so that's what they're doing here. And that's what this algorithm does. This is, if I remember correctly, I actually looked it up on Wikipedia, it's the finite difference formula. You know, it looks all complicated and mathy, but really all that this is doing is saying, you know, imagine you have a bunch of data over time. And so as a new value comes in, take that new value, this rt plus I plus 1, this value right here, take your new value, subtract your old value from it. So this is basically your previous value. So your new value minus your old value, and then divide that by the amount of time that was elapsed. And that's what's happening right here. So how much time elapsed between those 2 samples. And that gives you a rough estimate of the derivative of your signal or your value that's coming in right here. It's not perfect, it's not exact, but it's good enough. Now, the interesting thing is they tried it out and they were hoping that that would, like, maybe they'd graph it and they'd see this, aha, there's a nice big jump where every step happens, but they saw something like this, which is just as noisy and hard to follow as the data above here. So they actually abandoned this method. They didn't really do it in their algorithm. But it's kind of interesting to see that their thought process of like, well, let's, we've got a value, let's take the derivative and see what happens. Not a bad place to start sometimes. And so they didn't see anything that looked very promising here. So I actually didn't even bother implementing that because they didn't do it in the algorithm here. And so I didn't think it was worth the time to look at. So then they went on to what they call the step jerk threshold approach, where they wanted to look at basically, okay, it's still kind of interesting looking at that derivative, or what they call the jerk of your step movement. But rather than just looking at the raw value, look at what is the distance between a peak and a trough. So a peak is like, when your shoe moves all the way up and it's starting to move back down potentially, or maybe it's all the way down and it's starting to move back up. You're at some peak value and then it falls down and then it starts moving back again. And so you get down to like a trough value down here. So what is the distance between these peaks and troughs? Because you can see, for each step, there is like a big distance here. Here's presumably another step and there's probably a big distance there. Other steps, there's a big distance. Like if you look at this signal, it's kind of bounded by, on the lower parts here and on the upper parts here, they all kind of roughly hit the same peaks and troughs. So that distance is roughly the same in between there. And so they kind of wondered, like, well, okay, maybe that's important. Like if I look at that peak, that distance between my peak and my trough of my jerk signal, can I use that and maybe have a threshold that says, okay, once that distance gets big enough, because maybe if you're a really low step user, that distance might be kind of small, it might be bigger if you're a high step kind of user, but can I just look at that distance rather than the absolute kind of actual peak or trough values for that? And so that's what they ended up doing in this version, the peak jerk or the step jerk threshold version of this. And you can actually see the code for this. So that's the cool thing in this GitHub repository. Not only does it have the write-up and the paper, but all of the code is inside of here. And it's all Python code, so it's actually really easy to follow it. There's a main.py. This is in the sensor data folder of the GitHub repository. And by the way, I'll put a link to this GitHub repository on the video description when this goes live. But anyways, once this goes, so this is the main.py. This is what they use. It's a little bit weird. Basically, when you call this main.py, you give it a parameter that says what algorithm to run. And so they have all these names like AJPT, ASJT. This is the one we're looking at, is the adaptive, this is the one we're looking at, the SJT, the step jerk threshold. So that's the first one they tried. And so we can find the code for this. It's in this step jerk threshold.py. So if I go back to the code and I look at step jerk threshold.py, this is actually how they apply that step jerk threshold logic. And I'll just kind of summarize, because if you read the paper, it actually explains in a little bit more detail. What they want to do is figure out when you're in a peak, so from like this A to C period right here, B is kind of the peak. So as the signal's going up, figure out what is the maximum value in that peak, like what is the value B, and then look for the trough that follows that. So look for this C to E period right here, where the signal is below some threshold, and then figure out what's that minimum value, the trough, the minimum of that trough, that D value. And then figuring out the distance is just B minus D. So it's just the distance between there. So the thing is figuring out, when am I in this peak period versus when am I in this trough period right here? And then one kind of question is, well, okay, well, first of all, how do I know like difference between peak versus trough? Like what is this baseline value? And so they actually talk about the baseline is just gravity, just the force of gravity, with the shoes sitting on the bench like this, and with me not touching them and applying any forces, just gravity is pushing down on them, with the force of 1g. And so for me, my baseline value is 1, like 1 force of gravity with no movement at all, just standing still. I should see just 1g down against my sneakers. And then if there is some kind of movement, that might increase or decrease. I have to move more than the force of gravity to kind of move past it. And so that's what we can look for. If we set our baseline to 1, the 1G baseline, and in their paper they actually use a value of 10, so you can actually see this is their baseline. That's because they're measuring gravity in meters per second, and so the force of gravity is like 9.8 meters per second squared, usually the acceleration for it, so 10 is pretty close to it. Whereas for me, the way I'm reading the accelerometer data, I'm using this LIS x_g parameter, y_g, z_g. That's in the library for our accelerometer. We're converting from meters per second squared to gravities. So it's just a unit difference. Basically, my accelerometer data comes in the form of gravities, where 1G is equal to 9.8 meters per second squared. Whereas in the paper, they're just using the raw meters per second squared acceleration value. So their baseline is effectively 1G, which is 9.8 meters per second squared, or 10 meters per second squared, is kind of how they round it up to. So that's the difference there, but that's my baseline then. So 1G baseline. And so that's what I want to do in my signal then, is as I get new data points, look and see, is my new incoming set of data above 1G, which means I'm in some kind of peak period right here. And if I'm above 1G, if I'm in a peak, keep track of what is the highest value I saw during that peak. And then likewise, look for when I'm below that 1G threshold. So when my incoming values, when my filtered accelerometer magnitudes are below 1 or below 1G, then consider that a trough that I've moved into, and keep track of what is the minimum value, because I want to find the lowest value that I fall down into in a trough. And then I need to keep track of, okay, so what happens when I get through a full cycle of a peak to a trough and then back to the start of a peak again. So it's right at this point E right here where the algorithm kind of kicks in and says, okay, I've just transitioned from a trough to a peak. So let's go back and look at what was my previous peak maximum and my previous trough minimum, and compute that jerk distance value for that. And so that's what they do in this algorithm right here. And it's a little bit complicated in that they're building up data that they're going to graph in Matplotlib. So they're putting in some nice labels and things inside of here. But effectively what they're doing is they're enumerating all of the data. They're looking to see, is it below 0? And that 0 value is this gravity constant they set ahead of time. You can see right here. So, if my data is below that gravity value, then this is basically processing troughs. And you can see right here, this is where they keep track of the lowest trough value. And then this little bit right here, if my data goes above that 0 value, this is where I'm processing a peak. And so I want to keep track of the maximum value that I see within a peak. So that's what this first little bit does, is it's just figuring out, am I in a peak, am I in a trough, and then what's my min and max values. And then this little bit right here is looking for when I change from a trough into a peak. Basically, when my state changes, as I'm moving up past that 0 value, past that gravity value, then look and see, okay, what was that difference? So it looks to see, if I'm just exiting a trough, which means I'm going into a peak, then look and see, okay, what is the difference between my maximum value for my peak and my minimum value for my trough? And then literally the test to say, is it a step or not, is just if that jerk size, if that difference between the peak minimum and maximum, or the peak maximum and the trough minimum, if that's greater than some threshold they set, which they just set ahead of time as 1.5 right here, then fire off an animation, or consider this a step effectively. So it's really not too different from our step test algorithm. Our step test algorithm is just looking at the raw filtered acceleration value and applying a threshold, whereas this this jerk step detection is, instead of looking at the raw acceleration value, it's looking at over time, is the acceleration in a peak or a trough? Is it above or below a threshold? And then for each peak and trough, what is my minimum and maximum value? And then once I see a complete peak and trough cycle, what's that difference between the minimum and maximum value, and then apply a threshold to that. So that's kind of the difference there. And you can actually see that. That's a version of the code that I implemented. That's the Arduino step jerk test sketch right here. So I'll load this up and we'll look at the code real fast for this. Let's see if I open up, the step jerk test version of this. So this one, so it has a few parameters at the top of this one. So it has this gravity define, which I kind of mentioned before, and that's in the final version of this. this is that baseline level like I was talking about earlier. So this is just what is the normal force of gravity. This is how it knows when it's entering a peak, it's going to see gravity that's greater than this threshold value. And when it's entering a trough, that it's seeing gravity that's, or an acceleration force that's lower than this value effectively. So this is how it's differentiating between peaks and troughs. The threshold value here is just the threshold to apply to that jerk distance that we saw. So in their code, they use a value of 1.5. But because I'm using, my constants are basically like divided by 10. So, you know, whereas their gravity value is 10.0, mine's 1.0. So their threshold value is 1.5. Whereas mine should be 0.15 because I need to divide it by 10. So I'm just making my constant similar to their constant because my units are a different order of magnitude here. So that's why I have 0.15, whereas they have 1.5. It's just different orders of magnitude here. But that's really the two values that control this. Now, as far as the main loop goes, so here's the main loop of this step jerk test version. You can see it's really similar. So I'm grabbing the accelerometer data, I'm running it through that low pass filter, and then here is where I'm actually applying the step jerk detection. So what I do is I look at, you know, is this magnitude, oh, actually, I just noticed there's a bug in this code. Oh, cute. Wow, I didn't realize that this is kind of a major bug. I wonder if this changes it a bit. I'm actually looking at the raw magnitude. I'm not looking at the filtered magnitude here. Interesting. Well, let's fix this and see how this changes. But anyways, so for this sketch, basically, I'm looking to see, is my magnitude below that gravity threshold right here, in which case I'm in a trough, or is it above that gravity threshold right here, in which case I'm in a peak. So I'm just looking at, am I in a peak or am I in a trough? And I keep track of what was my old state, like what was the state in the last loop iteration, was it a peak or a trough? And then what's my new state, what's the current state based on the current filtered value? And then I can look and see, when does that state change? So when do I go from a peak to a trough state? And I actually added a third state. I have a 0 state. So if you happen to get a magnitude that's exactly 1.0 or that filtered value, you know, you're right at the borderline of maybe not moving at all, I just consider that a third state. In their code, they really don't care about it or deal with it much, but it's, you know, just makes it a little more obvious to the 3 different states you might be in, you know, peak, trough, or exactly on that 0 line. But anyways, that's what this code is doing. I'm just figuring out, am I in a peak or a trough? And then I look to see now, did my state change? So is my new state different than my previous state in this loop iteration? So this check is actually looking to see, is it the same? So, you know, if my state did not change, if I was in a peak in the last loop iteration, and if I'm still in a peak, then what I want to do is just look and see, you know, what is the peak value, and just keep updating, you know, the maximum value I saw during a peak and the minimum value I saw during a trough. And so that's what this little bit of code does right here. So if my state didn't change, then I want to look and see if I'm in a trough, then keep track of what is the lowest trough value. So I'm basically taking the minimum. I'm just looking at, here's my current value that came in, and actually there's a bug there. I'm looking at I want to look at the filtered value, not the raw magnitude. So anyways, though, but this is effectively keeping track of, you know, here's a new value that I filtered. You know, how low is it compared to the lowest value I've seen? And if it's not as low as the lowest value right here, then keep that old low value. But if it's lower than this old low value, then now set my low value down to that new value that came in right here. And same thing for the peaks. I'm just keeping track of what is the highest value, what is the lowest value that I saw in this loop. That's if my state doesn't change. If my state does change, so if I went from like a peak to a trough, or a maybe 0 to a trough, or 0 to a peak, or trough to a peak, you know, if something's different between these loop iterations, then this bit of code is going to run. And basically, I'm only looking at when I go into a peak. So as I'm going into a peak, and you know, I'm starting to see that upward movement, then let's go back and let's see, because my assumption is I'm seeing regular peak, trough, peak, trough, peak, trough. You know, I'm assuming that I'm not seeing like peak, 0, peak, 0. I would never see peak, 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 because that means my state's not changing. Like, it's not going to get to this block of code. It's still going to be running this block of code right here because my state hasn't actually changed. So it's really only when I go peak, trough, that this block of code is going to run right here. And what it does is it just looks at, okay, you know, I'm entering a peak, so I assume that I have a previous trough and a previous peak before that, and maybe there were some zero states, but I really even don't care about that. It's literally just that this last peak and last trough, that minimum and maximum peak and trough values that I care about. And so what I do is once I enter that peak, I compute, okay, for my previous peak and my previous trough, what is that jerk distance? So I just take the peak value minus the trough value. So this is the highest I ever got during the last peak and the lowest I ever got during the last trough. And so then that gives me this jerk distance value right here. And then I just look and see, is it above a threshold like this? And once it exceeds that threshold, then I just, I set this kind of timeout value, which says, okay, turn on all the lights. You can see it turns all the lights red, and then it will just slowly over time turn off the lights for this. And then the one little thing is I reset my my peak minimum and maximum, or my peak maximum, my trough minimum. So I set my peak maximum. I want to set that actually to my filtered value that I got. Basically, this is going to say, okay, you know, I've measured. I'm in a new peak measurement. So since this is the very first measurement in this peak, the largest value I've seen in this peak is the only value that I've seen in this peak. And so that's, I'm kind of bootstrapping, you know, my largest peak value is my current value because that's the only value in this peak right now. The next iteration of this loop, if it stays in a peak, it's going to keep updating that. It's going to, you know, as that peak value increases, it's going to keep increasing it. And then for my trough value, I want to reset this down to just a baseline value. I set it to the gravity value so that now when I enter a trough, basically a trough only occurs when I am below the gravity value right here. So I know for sure my filtered value should never be gravity or higher if I'm in a trough state, because this check would never be true. So because of that assumption, if I want to keep track of the minimum value I ever saw in a trough, if I start with the highest value that I'll never ever see in a trough, which is that gravity baseline, then it simplifies my logic so that, you know, I can just take the minimum value and I know I don't have to keep track of like, is this the first measurement? And okay, let's save this value or whatever. Just set it to some maximum sentinel value. And then over time, as real values come in, they're going to pull that minimum down to the lowest value for this. Okay, so let's save this. And this is actually the fixed version because I'm glad I caught that little bug. Interesting. I'll be curious to see how this changes the behavior, but let's load this onto one of the sneakers right here and see how this works. So I'm going to upload this code, and this is good. I'm going to actually have to change the other two versions of this code that we saw. So this might maybe slightly change the sneaker behavior. Okay, so this just loaded the sneaker code, and let's see how this looks. So, okay, so this is running the step jerk algorithm. So let's just see if I move this around. Not bad. You can see it's kind of on that downstroke that it's detecting the movement, and it's actually, so think of it this way, you know, as I'm moving it up, that's going into a peak, and then as I'm moving it down, that's going into a trough, and then as I go from trough back to peak, so it's that, you know, I'm at the very bottom and then I start moving up again, that's where it's actually hitting this state right here, because, you know, I was in peak down to trough, then starting to go into peak again. And so that's why you see it kind of turns on, you know, right when I'm at the bottom of the step and starting to pull back upwards again. And that's because, you know, it's detecting that change from peak to trough, and it's lighting it up, and it's seeing that difference there. So it's kind of nice. And, you know, if I take these nice moderately sized steps, it's able to detect that. And it seems pretty good. You know, if I'm just kind of holding it like this, nothing's really happening. If I take soft steps, let's see what happens. So see, nothing is happening. So that's kind of the, well, it detected that step. But yeah, you can see like it wasn't really doing much though before. So I just take nice little soft steps. And actually, if I put these on my feet and walk around with them, I notice that behavior. So if I take nice, good steps, it'll light up and I'll see what I want. But if I just take very small, shallow steps, it doesn't detect that. And so that's kind of one of the problems of this algorithm, or of this kind of iteration of the algorithm, is that, you know, you have to set this magic threshold value right here. And this value of 0.15, you know, it works well for a moderately sized step. But for a more shallow step, I would need to decrease this value to detect that. Or if it was too sensitive, if it was always firing, then I would need to increase this value potentially. So it's not much better than the first version of this algorithm that was just looking at the accelerometer, the filtered value, and then applying a threshold to it. I still have some magic threshold I need to set. It is kind of interesting though, with the first version, with that threshold version, it would sometimes detect steps on the downstroke and on the upstroke. So like you would see, as you move it, you might actually detect 2 steps. Like it would fire off as it goes up and would fire off as it comes down, because it sees a big impulse and acceleration up or down. Whereas in this version, it's a little bit smarter in that it only fires off when it's down and starting to go up. So you kind of get that 1 step movement. Whereas the filtered threshold version that we saw in the first video, that one might detect 2 steps. It might detect your upstroke and your downstroke. This version effectively only detects 1 step, because it's looking for the change from downstroke to upstroke and then applying a threshold to that. So it's a little bit better of an algorithm potentially. But let's see if we can improve on that. So that's the jerk step version that we looked at. Let's go back to the paper. So and they talk about it, they apply it to their data set, and they saw for one of their users it worked really well, and like these little red dots are where it detected all of the steps. And then for the other user, unfortunately, they had more shallow steps and it didn't detect it. So they went on to refine it a little bit more, and that's actually where we're going to get to the final version of this, the adaptive step jerk threshold. And basically their thought was, we think we're onto something, we've got a good idea here. Just the trickiness is, how do we set this threshold value? There's not one single value that works for everyone. Can we change that value over time? Like, can we pick a starting threshold, and then over time, as we see these cycles of peaks to troughs and peaks to troughs, and we're measuring that jerk step distance, can we adjust that threshold value so that if I'm constantly seeing a lot of these peak trough transitions with very small jerk steps, then I should probably assume that these are shallow steps and just lower my threshold to be within that range of values. And likewise, if I start seeing really strong steps, peak trough transitions with really large distances between the really large jerk step values, well, then maybe I should start increasing this threshold so that I become more sensitive, or maybe less sensitive to small motions, and I'm more sensitive to just these larger motions in that case. And so that's what they did, and they actually show in this algorithm, they effectively keep a running average. So every time so basically they start with a magic threshold value. So they actually start with the 0.15 value, or in their case it's 1.5. They start with that same value, but every time they detect a step, they look and see what is that jerk step distance, how does it compare to the average value, and then they update the average value based on that, on the new value that they saw. So that if that jerk step distance starts to get larger and larger and larger, it's going to increase the average value, and that average value becomes your threshold, so that your threshold increases as your jerk step distance increases. And then likewise, if your jerk step distance decreases, that's going to decrease that threshold value, and it's going to decrease your threshold that you're checking against in this case. And they're looking at, basically, they set a range. So if your new jerk step value is within like 65% of the previous jerk step, or the average jerk step value that you've seen before, which is kind of your current threshold. So if you're within 65% of that, then it considers that a step, and it will start updating the values. And so that's how it can catch, like, if you take really strong steps and then you start slowing down, as long as your steps start to be, like half as strong as the previous steps, it's going to figure that out. And so that's what they show in this algorithm here, and they actually have in the code here. And it's kind of funny, they have 2 versions of the code here. They have adaptive step jerk threshold old.py, and then this normal one, adaptive step jerk threshold.py. If we look at the old one, it's actually exactly like they show in the paper. And so they're applying this, they're computing a running average by just keeping track of like what's the total sum and the number of jerks steps that they saw, and then using that to compute a running average. But it's kind of interesting, if you look at the adaptive jerk step threshold.py, which is the one they ended up using in the paper, it's a slightly different computation inside of here, where they're actually computing a running average and standard deviation of your jerk step values. And they're basically using that to blend in your new jerk step value with this average, so that if you get a really strong jerk step that's some number of standard deviations beyond your average, that's actually right here, this check right here. So this jerk value is your new incoming jerk step distance. And then jerk mean is basically your average jerk step that you've been computing over time. And it just starts with a fixed value. They start with, if I remember, a value of 1 effectively. So they're just saying, hey, just here's gravity, or just a normal kind of starting value. But if your incoming value is greater than your average value, within a margin of some number of standard deviations, and so that's what this -4 times jerk deviations, or jerk dev, this jerk dev value is keeping the standard deviation, which is basically, standard deviation is given us a set of data points. You can figure out the average, which is, what value is maybe, the average value, or the mean of all those data points. But then your deviation is kind of, for each data point, how far is it from the average, above or below? And so it's a useful statistical concept. And they're basically looking to see if my incoming value is greater than some number of deviations from the average, which means that, like, this is an outlier. If I get an incoming jerk value that's like way above or way below my my average value, then that's important. It's something that's basically telling me, hey, this might be a step, or like this is something that was a big enough change to do something about. And so that's what happens in this algorithm right here. And they're actually, these two lines right here are kind of blending the, they're keeping this running average and this running standard deviation, but they're not just taking the new incoming jerk value and making that the new standard deviation or the new average value. They're using some coefficients, some weights effectively, so that they only take a little bit of the incoming value and they use that to slightly modify your average. So it's like a weighted running average of the standard deviation and the mean value that they're keeping here. And you can see the constants they use right here. So for the average, they only take 0.125. So basically, they're taking 12.5% of the new jerk value. If it's a really strong jerk, they'll take 12% of that and blend that into the average. So it's going to, increase it or decrease it by 12%. And then likewise for the standard deviation, they're also using a weighted value there, so that for a new standard deviation or for a new strong value, they're only going to take a quarter or 25% of its value to change that standard deviation. So I found it kind of interesting because the paper doesn't actually mention that algorithm. So the algorithm they described right here is what's in the old .py, whereas in this new version that they're using, they're actually using a weighted average and a weighted standard deviation to work. Both are really similar. The old code, I didn't look too deeply into it, but it looked like they were keeping a running average. They weren't using the standard deviation in this. Whereas here, they're also keeping a running average, but it's a weighted average rather than just like this standard kind of running average algorithm. So, I mean, they're doing the same thing. It's just slightly different, I think, in how they implemented this. And maybe they tweaked it and just didn't get it into the paper here. But that's what I ended up implementing, is I actually implemented this version right here that keeps a running standard deviation and running average. And then it uses some weights to blend in the new jerk step values. So when it sees a really strong jerk, it will update that average and that standard deviation. But the way it figures out if something is a strong jerk is basically looking at how far away a jerk is from the old average, and is it within some margin of the standard deviation to that value. So it will tune itself over time effectively. As I take regular strong steps, that's going to drive up the average to some large value, and then the standard deviation is going to settle at some kind of nice fixed value. If I'm taking regular steps, they're all going to be roughly probably a similar kind of standard deviation from that average value. But then if I change how my steps happen, if I take softer steps, they might get lower, and so I'm going to be further away from that average value. And once I get some number of standard deviations away, then this logic kicks in and it starts considering something a step and it updates it. Okay, so this version of the code is the adaptive step jerk test in the GitHub repository. So let's load that up, and I'm going to need to make the exact same fixes to that version also. So if I load this one up, let's change So this one, I'll mention real quick too. There's some defines at the top. So there's this initial jerk average is what I call it. This is the starting value for your average. This is like your starting threshold. And it's the same as the other sketch. You know, in the other sketch, I just had a fixed threshold that never changes. In this sketch, it's the same value, but this is just the starting point because this is the adaptive algorithm, and it's going to change this value. It's going to increase it and decrease it over time based on how your average step changes. Then I also have the alpha and the beta parameters. These are the blending parameters for how much the jerk step average should be changed and how much the standard deviation should be changed. It's not technically the standard deviation. I think this is the variance that they're computing. So I'm sorry, if you're a statistician, you're probably freaking out right now because I think the standard deviation is the square root of the variance, whereas I'm not actually computing the square root. So okay, maybe this is the variance. But anyways, these are just weighted averages. So these control how much, you know, I've got this new really strong value, but I don't want that to like completely override my old average. You know, I want my average to slowly change over time. And that's why these values are kind of small. So I just take a little bit of that new value and I blend it into my old value. And so that just means my, you know, this jerk threshold up here is just slowly going to increase and slowly decrease over time as my steps change. Okay, so for this version, let me make those same fixes that I made before. So it's the filtered value, not the raw magnitude that I want to compare against here. So that and that. And then let me just double check here. I think we should be all good. That's the one I want right there. So, okay, so that's it. You won't need to make these fixes. I'll push this up on GitHub. Okay, let's save this and let's load this version onto the shoe and see what happens. So let's see, I'll connect it up and let's upload this sketch. And then we'll see, and again, this isn't gonna do any animation, it's just gonna light up red. So we'll see what happens. Okay, so it's done like that. And so this is kind of cool. Okay, so it's running right now. And now remember, so it starts out with that 0.15 threshold value, the value that we saw way at the top here. So that's kind of the threshold that it starts with, but it's looking at, and it also starts with, I have an initial standard deviation value, which I didn't make it a define. I just take half of that starting average value. So basically it's half of this value. So when a jerk value comes in that's more than half of this initial value, then it considers that a significant jerk, I would say, which means that, you know, it's a jerk that should be considered a step. And then it's going to go and it's going to update that average and blend in kind of the new jerk value. Let's just see how this thing kind of looks. So you can see as I take kind of strong steps, again, it's lighting up kind of right as the downstroke ends and right as I start to move back up again, because it's detecting that change from a trough to a peak, and then it notices that it's a strong step. And so it's nice, and it's detecting that really, really smoothly, very nice and regular. Let's see what happens if I take kind of shallow steps. So this is kind of nice. You know, remember before, just a moment ago with the previous version, when I did these shallow steps, it wasn't detecting this at all. You know, it had no idea. But then I go back to take these strong steps and then shallow steps again. And you can see it's a little bit sensitive when it starts doing the shallow steps. That's because that average takes a little bit of time to change. So it's like a really strong average from these really strong steps that are happening. But then, you know, these shallow steps start to happen. And so it might detect things, you know, more than it should at first. But as I'm just consistently taking these shallow steps, it will adjust itself down so that now it's, you know, at a low threshold. And so it just detects kind of that upward movement from a very shallow step. So this is pretty good. I'm really impressed with this algorithm at this point. Like, it's working really well and able to detect these steps. And actually, this is working better now that I fixed that bug. I just noticed it seems to actually really be spot on. And so the bug actually that I just fixed there was I wasn't using the filtered value, I was using the raw value. And so that means it was a little more sensitive because it's getting that noisy acceleration value, whereas now it's just getting that 3.66 low pass hertz filtered value. And so this is actually even better than it was before. So this is really cool though. Like, we're using that adaptive algorithm now. And so let's just, I'll show you the code real quick for this. There's really not much that's different. Here's the main loop again. So here's my main loop, and actually here, I'll just close the old versions here so it's less confusing. So here's the main loop. Here is kind of where I'm grabbing the accelerometer value. Here is where I filter that. I print it out if I want. And then here is where I do that jerk detection. And again, it's exactly the same. I'm looking for, am I in a trough or am I in a peak? So I just look, based on, my incoming value, is it above or below gravity, that baseline gravity threshold? I figure out if I'm in a peak or a trough. Exact same code right here where I'm just keeping track of when I'm in a peak, what's my maximum peak value? When I'm in a trough, what's my minimum trough value? And then right here, exact same code. When I transition from a trough into a peak, go back and figure out what is the distance between that old minimum and maximum value from my peak and my trough. So that's happening right here. And now is where the code is a little bit different. It's actually these lines right here that are different, and these match what the paper, what the code from the paper does right here. And so we'll just kind of dig through this real fast, but basically I'm looking at, okay, what is my current average jerk step value? And then subtract 4 times the variance or the standard deviation or the deviation of it. Take 4 times my variance, subtract it from that, so that this is giving me some threshold value that says, okay, I will accept any jerk that's within 4 standard deviations or within 4 deviations of my average jerk value. So that just means that if I get a jerk value that's coming in, that's, let's say my average is right here, and I get a jerk value that's, coming in like right here, like really close to it, then I will accept this as a new jerk step. But maybe I get a jerk value that's really low, and maybe my standard deviation values only come down to about here. I'm going to reject it because it's not close enough. This was too light of a step. It must be noise. I don't consider this a change that's significant enough to consider this a step. So that's kind of what's happening here. Is I'm just looking to see, is my incoming value within some number of deviations from my average value? And if so, I've detected a strong jerk is what I call it. And then I'm going to update. Okay, first I update my deviation, or I call it standard deviation, but again, it's probably variance. And so I'm using the exact same algorithm that they have in their code, where you figure out, okay, what is the variance? What is the distance from my incoming value and my average? So I take my average minus my incoming value, take the absolute value of that because it might be negative, and I multiply that by the beta value. That's that blending weight. So I just take some percent of that new deviance value, and then I add that to the inverse percent of my old deviance value. So this is my old standard deviation value, and I'm just taking the inverse, or 1 minus beta. So if my beta value up here is 0.25, then 1 minus beta is 0.75. So just think of it as, beta and 1 minus beta are going to add up to 1. So I'm going to get, if I add 2 values that are multiplied by beta and 1 minus beta, I'm going to get a single value that's, close to the value that I want. Like, I'm not going to double my value because it's effectively kind of like multiplying it by 1. But it just gives more weight to one side of this equation. Basically, on this side, I'm going to take 75% of the old standard deviation, or this jerk deviance value, take 75% of that, and then I'm going to add 25% of the new standard deviance value. And so this is where this kind of blended, weighted, kind of moving standard deviation applies to this, and so how it kind of slowly changes over time. And the exact same thing happens to the mean or the average value. So they just take your current jerk value and they multiply by this alpha coefficient, which is 0.125. So I'm taking 12.5% of my new jerk value right here. And then I'm just blending it with the 1 minus alpha. So instead of 12.5%, this is now like what, 87.5%. So I'm taking 87.5% of my old average value. So this is preferring the old average, but it's still letting some of the new average be added to it, so that, over time, if that new average keeps falling and falling and falling, it's slowly going to lower that value. But it just means that, if a really strong step comes in, it's not going to immediately change that average value. It's not going to throw everything off. It's only after like 5 or 10 really strong steps occur will that average get slowly pushed up to a much higher threshold value for this. So that's what's happening here, and the rest of this code is exactly the same as before. So that's no different. It's really just a change to how I'm considering when a jerk or a strong jerk occurs, and then how I use this kind of weighted average and weighted deviation or standard deviation or variance to control my detection of these strong steps. So that's it as far as the basic code. Now the paper goes on a little bit further, and they actually go on to another method, and they said that this worked pretty well in their testing, but they did notice some cases where if you go from like running to walking to running to jogging to walking, and you see like these big differences where, you know, you have really strong steps and then really shallow steps. That transition period, so like right here, if you're looking at this data, you know, imagine right here, maybe they were running, and so they have these really wide steps, although you're not actually supposed to run with a long gait. You're actually just supposed to use a short gait when you run. But let's say they're running right here, and then right here they have a really small gait, so maybe they're just like tiptoeing right here. In this little transition period right here, you know, their average has been influenced by all these previous really strong steps. So you can imagine that average has been pushed way up. You know, you've got to have a strong step. But when they start tiptoeing, that might not be strong enough. And so it's probably missing some of these early steps because that average has been influenced by all these previous values. And over time, you know, if they tiptoe long enough, it's going to slowly pull that value up. But they went on to refine this a little bit more, where they keep a buffer of just some number of previous values. And so they actually just keep a running average that only looks at like the last 20 readings, if I remember correctly, so that it's a little faster to react. So that, you know, if you had a bunch of strong movement in the past, that will get ignored 20 times in the future. You know, once you get past that buffer, that data just goes completely away and you don't even use it anymore in the computations. You know, I didn't really think that was necessary, because as I was playing with this, like it's pretty good right now. You know, you can see as I move my steps around, it seems to work well, and it works even better with the little bug fix I made. So, you know, for now, I didn't go forward to actually add this buffer to it. They did even more also. They mentioned they look at the pace, which is the amount of time that a peak trough cycle takes. So they were looking at, you know, measure that amount of time that a peak trough takes, and then look both at the distance between the peak trough and the time that elapses. And they use that to also, and they also apply a similar adaptive algorithm to that uses the average value and adjusts it over time. But again, I think that that's maybe more complexity than I need right now for this. I think it's probably good enough as is. So let's go back to that the Circuit Walker version of this. So let's go back to the Arduino Circuit Walker. And I'm going to make that bug fix that I made earlier because I just want to see how this changes it. So let's go back and let's add that filtered value. So right here is where I get the filtering for my accelerometer. And I want to use that value instead of my raw magnitude. So let's put that in there. Let's put in filtered right here. And then there's one other filtered value that I need right down here. So let's save that, and then let's load this onto the shoe just because I want to see how that looks. Okay, so let's upload that. And then real fast, I guess I'll go through the animation effect just real quickly, because we're about an hour and 10 minutes into this stream. I only want to go maybe 10 more minutes or so. Okay, so that loaded up. But I'll show real fast how I do this little animation, because I'm just doing a sine wave, which I've done in a million other videos. That's kind of my favorite thing. Well, let me load up this one also with the same fixed code, because this sneaker below the other sneaker right here, this is running the buggy version that was using the raw filtered value. So let's load up this fixed version. And so now I'll have two consistent sneakers. And let's see what they look like. I'll see if I kind of move them both around, how it looks. And actually, I have a little video of me actually walking with these, so I'll show that in a second here too. Okay, so we've got both of these. And so now if I hold these up, let's see what happens. So, you know, imagine I'm taking steps, and you can kind of see as I take steps, it's on those that upward movement that each one kind of fires off. And I can take strong steps, and it seems to detect them. It's actually kind of hard and confusing for me to watch and move these. And I can take shallow steps. You know, if I take shallow steps like this, then it's starting to detect that movement. So pretty cool. It's adapting itself to that value, and it's lighting up, and it's doing, I would say, quite a good job of detecting steps. I'll show real fast. This is a little video. I don't think you're going to hear any audio from this, which Doesn't really matter, to be honest. But this was just me wearing the sneakers, and I'm not even sure if this is going to play super well, if this screen capture is going to work. But you can see, I'm standing in place, and it's detecting the movement. And then as I start walking here in a second, I think I'm showing off the sneakers right here, these cool kind of circuit board Chuck Taylors. But I'll start walking, and then you'll see it starts detecting. It's kind of funny. The left shoe is a little more sensitive. I'm not sure why. I think maybe because I had it more strongly connected, like the zip tie was tighter, and so maybe it's picking up more movement. Like as I moved my leg, it was starting to get some false positives. But again, it was running that slightly buggy version of the code. So I would bet if I try it now, it's maybe a little bit better. But this is cool. I mean, notice every step, it's like boom, it's lighting up, it's flashing, it's noticing that change, and then it slowly goes away like that. So pretty cool. I love how simple this is, and that you just put this Circuit Playground board onto your shoe, and that's it. You don't have to glue, a strip of NeoPixels onto here. You don't have to mess with putting Velostat inside of here. It's just the board and everything is all ready to go with that. Okay, so like I said, for this animation, real fast, I'll just go through. At the top of this sketch, there is an Animate Rainbow function, and this is basically called in the main loop. So in the main loop, I look to see this Pixel Clear MS. This is kind of a timer or a counter that says how many milliseconds should the pixels be animating for. And when I detect a step way down here, I basically say, okay, I've detected a step, start animating my pixels. So set that countdown to some fixed value, which is set in the defines up above. And so that's this value right here, so like 500 milliseconds. So when I detect a step, I set a counter that says, okay, for the next 500 milliseconds, animate the pixels, do something cool, make some rainbow animations or whatever. And so that's what's happening in the main loop if I go back down to this point right here. And so every loop iteration, it just looks to see how much time elapsed since the last iteration. It subtracts that from my counter right here. And then if my counter gets below 0, then I know I've elapsed enough time that I should not animate the pixels anymore. So I actually just turn them off at this point. But if I have not elapsed all of that time yet, if there's still some time remaining for my animations, I compute how much time has elapsed. And rather than a value in milliseconds, I actually compute this as a value from 0 to 1, where at value 0, I haven't elapsed any time at all. I just started that animation. And at a value of 1, I'm done animating. And so, I don't know, like, was it 500 milliseconds? Was it 200 milliseconds? Was it 2,000 milliseconds? I don't really care. As far as my animation is concerned, it just needs to know when it's done. It's going to use this elapsed value from 0 to 1 to slowly fade out. So just as that value goes from 0 to 1, it can fade out the pixels. And so that's why you kind of see as I move these things around, they get bright with the rainbow colors, and then they kind of fade back down to black. And so that's what's happening here is as that 500 milliseconds elapses, this elapsed value gets computed from 0 to 1 and eventually gets to 1, and it's fully turned off. They're not lit up like right now. So I'm calling this Animate Rainbow function though during this animation cycle. And so that's up at the top right here. And really all that I'm doing inside of here, I'm just going pixel by pixel, and I'm computing a sine wave value. So sine wave just goes up and down at some regular frequency. And so I'm using the frequency that's defined at the top right here, this animation frequency in hertz. That's the frequency of my sine wave. So basically, as this frequency increases, it just means how many times does this sine wave go from -1 to 1 each second. So, if that frequency value is 1, it just means in 1 second of elapsed time, I'm going to go the full cycle of my sine wave. If it's a value of 2, then in 1 second, I'm going to go the sine wave twice. So it's going to be faster. And basically, so I'm using that sine wave to figure out, to get a nice value that changes from -1 to 1. And I'm offsetting it at each pixel with a phase value. And this just comes back to, if you look at the equation for a sine wave, there's one component right here, which is your frequency and your time. And then you can also add a phase to it to just shift the starting point of the sine wave. So that basically, instead of each pixel lighting up the exact same color, and then it's slowly maybe changing over time through all these rainbow colors, each pixel is offset slightly so that you see the rainbow move around the pixels. Rather than all of the pixels light up the same color, I adjust the phase so that at each pixel I change the phase. And the phase goes from 0 to 2 times pi, because it's basically 360 degrees, or like 2 pi radians in a full cycle of the sine wave. And so I just figure out for each pixel, for pixel 0, it has no offset. For pixel 1, it's 1/10, because there are 10 pixels on this board, it's 1/10 of a full circle, or 2 pi radians. And so that's what this phase computation does. For the second pixel, it's 2/10 and 3/10 for the next one, and on and on. So this phase just increases, and so that changes the starting point of this sine wave, which means that each pixel now has an individual kind of up down -1 to 1 sine wave value that it gets. And then I'm just using linear interpolation to say, okay, my sine wave is going to give me a value that goes from -1 to +1. It's just going to always change in between -1 and +1. But I want a value that goes from 0 to 360, because I'm going to use this value as the hue, because there's a different color space. Instead of the red, green, blue color space, I can use the HSV, or the hue saturation value color space. And the cool thing about the HSV color space is you give a hue value that's in degrees from 0 to 360, and that controls the color. So, and that controls everything. Like for the color red, there is a specific hue, I think hue 0. For the color orange, it's like 35 degrees of hue. And if you can look up on Wikipedia, it'll actually show you there's a color map that shows for all the hue values. And then if you want like a bright red, then you control the saturation and the value, the S and the V parameters of the HSV color space. So if you want like a half bright orange color, well, your hue would be 35, but your value, your V value, would be maybe half, like 0.5 instead of 1. So that's what I'm doing ultimately, is I made this set pixel HSV function that takes a hue saturation value color, an HSV color. I'm modulating the hue, the H value, with a sine wave that changes over time and based on the phase of each pixel, or based on the position of each pixel. So I'm just going to modulate that. So my sine wave, instead of going from -1 to 1, it goes from 0 to 360, because that's what my hue values are supposed to be right here. That's what this lerp, or this linear interpolation function, will do. It converts a value within that -1 to 1 range into a value that falls within the 0 to 360 range right here. So I compute my hue within that range. So now my hue is going to animate over time and based on pixel position. And then to make it fade out, the nice thing is with that HSV color space, if I want to fade out or like slowly turn off or dim the color of something, I just need to change the value, the V parameter. So the S, the saturation, I always want 1. That's full saturation. I just want the full color brightness. But then the value lets me control whether it's dim or bright. And so I'm just taking the inverse of the elapsed value, because remember, this elapsed value, it's going to start at 0, and then after 500 milliseconds have elapsed, after my animation has finished, it's going to increase to the value 1. So once it's at a value of 1, then my animation is finished. So basically, when I start with a value of 0 in this elapsed time, I want full brightness. So I do 1 minus my elapsed time, so that at the initial start, I'm going to have a full 1.0 value for my value of my color. And then once my animation maybe gets halfway into it, this elapsed value is going to be equal to 0.5. It's going to be equal to half. So I'm going to have 1 minus 0.5. So I'll get a value of 0.5, which means my value, my V parameter to my HSV color is now half, which means half as bright. And so it's faded out half as much, or it's half as bright as when it started. And then eventually this elapsed value is going to get up to the value 1. And once it's a value of 1, 1 minus 1 equals 0. So I'm going to get a HSV color with a value of 0, which means black, nothing, turned off effectively. So that's why, as I move these around, you see they start out strong and then they fade and they turn off down to a black color. And so that's what you're seeing there, is that elapsed value goes from 0 to 1, which makes the color value go from 1 to 0. So I'm just inverting it effectively here. So that's all that's happening right here. And there's some other functions in here. This HSV to RGB color conversion function, I use this in a lot of sketches. It's something I found on the web that's really handy. So this is just converting, because NeoPixels expect color data in red, green, blue format, whereas for me, it's easier to do the math in this HSV color space and then convert to red, green, blue colors so that I can make this work a little more easily. So that's it. That's all that happens in the animation. Again, the jerk step detection is all the same that we saw before. I'm just basically, once I detect a step, I just set this timer or this clock that says, okay, start animating the pixels, and then it will every loop go through and figure out how much time elapsed and then drive the animation right here with that. So that's it. That is the Circuit Walker Sneaker project using the adaptive jerk step detection algorithm. And I definitely have to give a lot of credit to the folks that wrote this paper, Dan Murray and Ryan Bonnick. So this was, super handy because, it's great that they have the code and the actual explanation here. So I could go through, and I went through the exact same kind of derivation that they did effectively. So I started with a simple accelerometer magnitude that I filter and then apply a threshold to. And we saw that works, but you have to tune that threshold so that if you're a strong stepper, you need a specific threshold, but if you're a light stepper, you need to lower that threshold. And then we moved on to look at, okay, well, what about looking at the jerk step distance? So instead of just looking at the filtered acceleration, look at the peaks and the troughs and the distance between the peaks and the troughs, and then apply a threshold to that. And so that one worked a little better in that it was able to detect, only on the start of an upstroke do I actually detect the movement. So, notice how this thing turns on right as I start to move back up. It doesn't really figure out as I move down. It's only when I'm moving from down to up. Whereas, the simpler one, just the filtered threshold approach, was detecting both the up and the down. So it's kind of nice that, the next little evolution was a little bit smarter. It was detecting, maybe just one part of this step, but it was still hard because you had to have that magic threshold value, and so it still wasn't able to detect, the difference between a strong stepper and a light stepper. And then finally we ended on the adaptive version here, where we use that average and that deviation, standard deviation value, and we adjust them over time with a weighted average. And we use that to set a new threshold. So we will change that threshold up and down based on the jerk steps that we're measuring for this. And so really clever, very smart way, I think, to do this. And that you can see the code is not so complex that, I can't do this in Arduino. It's just a little bit of math, basically. There's almost no memory that I'm using here as far as, I'm not keeping track of like all of these old measurements and things. I'm just keeping a running average and a running standard deviation. So, this is all the memory that I'm using right here. The filter has to keep track of some of the old values, but it's actually pretty impressive what this can do. So really cool thing that I think these guys put together with this, and I was able to adapt this to a version of the Firewalker sneakers here, the Circuit Walker sneakers that we made. Okay, so if folks have questions, throw them into the chat, and I'll see if I can answer them. And let's see, I'll jump back to the main view real fast. Yeah, I don't see a lot of questions, so I'll probably wrap this up because it's starting to run a little bit longer. So like I said, this is part 2. I did a part 1. Check out part 1 where I did a bunch of the filtering. I showed how to build that filter. In this part 2, we saw the final version. These are the Arduino versions of the Circuit Walker sneakers, but I'd like to do a Circuit Python version of these sneakers. And so, maybe next week we'll see if I can do a Circuit Python version. The Circuit Python version is going to be more difficult because there is a lot of math that's happening here, like that low pass filter. You saw that adaptive jerk step. It's doing a lot of computations in that loop. And so it's going to be harder because the Python version of this, it's going to be slower at doing that math. So I'm going to think and see, just intuitively, I kind of assume I'm not going to be able to do the exact same algorithm in CircuitPython on the SAMD21 at least, because I'm assuming I'm not going to have enough speed to do all that math, because I need to apply that low pass filter and I need to do that jerk step detection and all that stuff. So let's see, I have some ideas. We'll tune in next week and we'll see if I can make it work in CircuitPython. Maybe using some of the features of the accelerometer. It might not be exactly as good as the Arduino version, but I think we'll get pretty close with this. So cool. Let's see. So question-wise, let's see. Yep, I don't see any questions in here. So I will end the stream. Check out Twitch or check out youtube.com/Adafruit. You'll see this video. And again, all the links will be down in the description below to the code that you saw here, the paper, everything I've talked about, the previous video. I'll put a link in there. And then check out youtube.com. Yeah, check out youtube.com/Adafruit to see this video. Check out twitch.tv/Adafruit. That's where I like to stream these things live. Every Friday I like to do a live stream. And if you like this, click the like or the comment, the subscribe, and let us know that this is useful stuff. and I'll keep making content like this. Until next time, thanks a lot for watching. This is Tony from Adafruit with the Circuit Walker Sneaker Project. So I'll see you guys later. Bye.